Hello everyone, Miss Katongo here. This is another physics related problem, but before we get to the problem that has been displayed on the screen, don't forget to like and subscribe to my YouTube channel. Let's get to the problem. An object of mass m is connected to two rubber bands of length L, each under the tension F, as in figure 13.72. The object is displaced vertically by a small distance of y. Assuming the tension does not change, show that the restoring force is negative 2F over L times y, and the system exhibits simple harmonic motion with an angular frequency of that. So, we are told that this mass has been displaced vertically from its original position to a final position, which is here. Okay. And therefore, due to the displacement of this ball, it will create some tension in the string. And this vertical displacement is termed as y. And due to it being displaced vertically, we will have the force that will act in opposition to the displacement, which is known as the restoring force. Due to it acting in the opposite direction, it will bear a negative. And it has been, rather, this ball has been displaced at an angle of theta and at an angle of theta, where we have the line, the length L, and as well as L. So, isolating one part of this diagram, rather, we will have the ball there and the length L, and finally the displacement, the vertical displacement, which is y. And we'll have the length being L, and finally, due to it being vertically displaced, we'll have a tension over there, and finally the tension being F, of course, and finally the restoring force acting in opposition to the vertical displacement as F R force, bearing a negative, of course. So using SOHCAHTOA, we can have the restoring force, rather, in form of the sine function. So we'll have the sine of theta is equal to the opposite, which is negative of FR, over the hypotenuse, which is the tension F. Therefore, the tension F will be given as F sine of theta is equal to the negative of the restoring force, where we have the restoring force being equal to negative of F sine of theta. Now, remember that this part of the diagram was an extract of the main part, which is this part. So therefore, we have to account the other part of this displacement. So hence, we will multiply it by 2 so that we can have the summation of the restoring force being negative 2 F sine of theta as our restoring force. Our theta, therefore, will be in terms of the vertical displacement, and the length being equal to the tan inverse of the opposite, of course, being y, over the adjacent being L. And so, since this displacement shown is only a small displacement we'll have our sine theta being equal to tan theta. And if we have our tan theta, we'll have it as our y over our L. Now, if I can get rid of this part, substituting this in our equation, we'll have the FR force, which is equal to negative 2F, which is the tension, sine theta being equal to y over L. And finally, our restoring force FR being equal to negative 2F over our L multiplied by y. So hence proven. Now let's go to the second part of the question. So the second part of the question says, show that the system exhibits simple harmonic motion. Show that the system exhibits simple harmonic motion. We have found the restoring force FR being equal to negative 2 the tension F times the displacement y over the length. Okay, and therefore, according to the second Newton's law of motion, it says force according to the equation is equal to mass times the acceleration. So we can replace the restoring force with this. So therefore we'll say MA is equal to negative 2Fy over our L, making A subject of formula. We'll definitely have our acceleration A is equal to negative 2F over L y over M. Okay, now from our simple harmonic motion, we know that our acceleration is equal to negative omega squared times that of the amplitude. Okay, so therefore we can replace our A in that equation so as to prove that the system is undergoing simple harmonic motion. So therefore, replacing this into our equation, that will have negative omega squared times that of the amplitude is equal to negative 2F over L multiplied by the y over M, which is the mass. Okay, so getting rid of the negatives on both sides, we'll have W squared, which is the angular frequency, times the amplitude is equal to 2F over L y over M. Now, okay, let's get rid of this. Now, we have to obtain the angular frequency from the simple harmonic motion equation. Okay, so then we know that the y displacement is the maximum displacement of the ball, or rather of the small mass. So therefore we can term or we can say y is equal to that of the amplitude. So replacing a as y, we'll have angular frequency squared times the a is equal to 2f over L y over m. Replacing a as y, we'll have w squared, which is the omega squared, times y is equal to 2f over L y over m. Getting rid of the y's, we'll have w squared, which is the angular frequency, being equal to 2f over Lm. Square rooting both sides of the equation, we have the angular frequency being equal to the root of 2f over Lm. Hence, proven.